Welcome to today's lecture for the 6th of April 2020. The topic today is special and highly appropriate for the period we're living in. It is the S-curve history of anything that spreads or is collected on an area. So the S-curve. The S-curve history for future of spreading and collecting. The S-curve is the observation that things that spread, the areas, for example, that's covered by a spreading virus, or the volume that's filled by a colony of living things, bacteria, coral, animal on the prairie, and all of that, that area, or the size of that population, increases in three ways sequentially over time. Here's the size versus time. The increase is, by the way, both start from zero. In the beginning, the increase is slow, then slow but increasing. The rate of increase increases itself, so there's acceleration here, and then later there is a monotonic decrease in the rate, which means deceleration, so that altogether the ascent or the growth of the size is represented by a curve shaped as an S. This observation has a very long history. It's about 200 years old. It comes from I believe the French army. It's called the logistics function. It obviously describes how things are distributed to the troops, how things are collected from an area, such as harvesting grain and putting it in sacks, or for that matter, collecting sewage from the city, collecting taxes from the taxpayers. You can use your imagination. Everything that spreads on an area or fills the volume is increasing in size this way. Of course, today we're living through the example set by the spreading of this particular virus, and which of course started from size zero, from one point in Wuhan, China. And now the spreading continues to increase all over the globe. So that's the phenomenon. Phenomenon means one word for observations that repeat themselves many, many, many times. Observations of the same kind. I gave you the spreading of not only of these living systems, but you can have here the spreading of milk on the kitchen floor, or the spreading of the rain on the territory in the form of growing river basins that have their channels swelling. Now, the lesson that recommends itself as a moment for this particular course is the act of predicting this behavior by invoking the constructor law. And that act starts rather simply. It begins with, making the simplest drawing, which is that of the area. And I pick a drawing that's two-dimensional. That means it has a length scale in one direction, L, and I picked the simplest such drawing, which has the same length scale, L, in the other direction. we'll call it horizontal, we'll call it vertical, even though gravity has nothing to do with what I'm discussing. And now the spreading involves something that's different than what is already on the area. In our case, the area, let's say, is dry. And what begins to spread is the water in a river channel, the bed of which was in the beginning dry. So we have a dry river bed. Of course, the rain is falling in the hills, and water begins to invade the dry territory. It invades it with a particular speed called v. And it starts doing this from time t equals 0, when the channel was just beginning to get wet. Time was t equals 0. When the whole channel is filled, obviously, time here is L over V. And so let's assume that we've watched the whole invasion going on from left to right. No, this is not the only thing that happens. The river banks are, as you know, filled with soil, which then, because of the water in the channel, becomes wet or muddy. And so on both sides, as the water advances, a finger of wet banks emerges. And this finger, of course, becomes longer, all the way to its longest configuration, which corresponds to the end of invasion. So this particular time means end of invasion. The terminology invasion comes from the military. A military invasion happens on a totally new area through channels. The invader attacks not with a front that moves parallel to itself. The invader attacks with points of, shaped as fingers, which penetrate the defenses. So the first conclusion is that the originally dry area has started to get wet, and if the wetness was all the way to location X, shown over the area that's been shaded, then we can calculate the size of that area so that we can plot it here. So the area that's shaded, I say shaded this way, is a function of X, and it is of order of what? The length, X, and the thickness of the finger. The thickness of the finger in boundary layer theory, because what this finger is, it's in fact the sandwich of two boundary layers, a sandwich stuck together along the very thin slice of meat. Delta. Now delta is the length scale in the transversal direction. That's delta. We know, so what goes on in the river banks is a phenomenon of transport of, in this case, wetness, known as diffusion. Diffusion. Diffusion in this case is the diffusion of water through the pores, also known as Darcy flow, or mass transfer, or heat transfer, or momentum transfer. Momentum transfer is the diffusion that occupies its own role in the so-called boundary layer theory of Prandtl. The point of the invocation of the phenomenon in this transversal direction of transport is that there's only one formula to borrow from the subject of diffusion. It is that diffusion, also known as the diffusion penetration depth, the scale of that is the square root of alpha and time. Alpha is the diffusivity. In this case, the diffusivity of water seeping through the sand or through the soil. Let's call it the diffusivity. And time is the time that it took for this particular finger to develop. That time is clearly x divided by v. So it is this that I substitute into the area estimate. I have x, and then delta, which is the square root of alpha x over v. Meaning what? Meaning that this area, the beginning of my discovery, increases in proportion with x to the power 3/3. The exponent 3/3 is greater than 1, which means that the arc of this curve in the beginning is accelerating upward faster than the curve with zero acceleration, which is the straight line. So a straight line would have had the slope of 1, meaning not 1.5. The other one, on a log representation, would have a slope of 3 divided by 2. Anyway, this particular formula, which I call the arc of invasion. So invasion is the first arc of the S curve, and it is deducible from this very simple argument. Additional formulas to remember. In fact, what's worth remembering, I'm putting in the upper right-hand corner of the green board. One is this, that during invasion, A of x goes as x to 3/2. The other is that the size of this area at the end of invasion, A at the end of invasion is equal, of order, this alpha over v to 1/2, and then L through to 3/2. And of course, the time at the end of invasion, which I wrote over here, is of order L over V. So this is what's worth remembering about the very first, the beginning of the S curve. Now, after I erase the blackboard, I will show you the continuation, how to predict the rest of the S curve. So now for the rest of the story. After the finger has grown to its biggest size, what we have is a picture that's relatively simple. It is one with two regions. Well, a picture that's dominated dominated by the rest of the territory, which is much bigger, and it is dry. This territory is dry. And in it, or into it, there is a steady penetration upward and downward as planes and planes of diffusion migrating downward and upward away from the wet region. In other words, the territory that has been wetted increases in thickness. And that increase in thickness has its own penetration distance delta, which is given by the same formula, the one that I erased, namely square root of alpha t. That means that if we are before I continue with the implications of what I drew in yellow, how is the rest of the area increasing in time? Because of diffusion upward and downward away from this central wetted channel with its river banks. Well, it increases like this. So the area of the so-called second phase of the growth phenomenon is called the area during consolidation. So this migration upward and downward is called consolidation. Consolidation, the word means becoming solid together, or putting solid in the holes that originally were empty. That's consolidation. And this area is, of course, as a function of time, is of the order of this delta, and then L. And never mind that we have two deltas, one extending upward and the other one downward. But as you know, in the banking and accounting and mathematics of scale analysis, 2 is 1. 2 is of order 1. It doesn't mean that if you score 2 goals in soccer, you are as good as having scored only 1. But here it means that the order of magnitude of this yellow area is what I wrote here. Of course, delta is, as I said, the square root of alpha t. And amazing, with almost zero effort, we have discovered that the remainder of the growth behavior is described by this formula, square root of alpha, and then t to power 1/2. So this is a curve that has its own, graph. I'm going to make it in another color, namely yellow. Has its own graph versus its own time. And this curve is concave because the exponent is less than 1. The previous one was convex. And I'm going to draw it. Now, that's the end of the second part of the discovery. Now, the punchline, which has to be delivered graphically because the whole story began with observations that are presented to us as a drawing, the drawing of the S-curve, is that the reality consists of invasion, followed by consolidation. How? Consolidation follows invasion smoothly. Consolidation is actually born out of the invasion. Without the invasion first, there's nothing to consolidate with. So here's the invasion. And the reality is that the second curve is a continuation of the first. We see that immediately, graphically, by sliding in time the second curve to mesh with the first at the point where the slopes are equal. And this is how the second half of the curve, of the S curve, is this portion of the so that's a slide. This portion of the consolidation curve. Now, the lesson has two reasons why it is useful. Number one, a universal phenomenon, the S curve, is accessible to you with pencil and paper. And the paper is the back of an envelope. So you can do it. That's the first secret you learn. The second is that this is just an introduction to the usefulness of your discovery. Meaning the rest of the story, the rest of the lecture has to do with usefulness. And of course, usefulness can take in many directions of investigation. One, well, it depends on what is spreading. What is spreading, in some cases you want to facilitate, in other cases you want to thwart. So, excuse me. And so, to facilitate means to have an S curve that's rising faster and to a higher level. That's called usefulness Roman 1, facilitate. The other direction, as in the case of fighting an epidemic, it is to obstruct. Obstruct. So that's to facilitate. The other one would be to obstruct. Roman 2, to obstruct. And I propose we talk about both directions of usefulness. Why? Because it is quite useful to do so. Now, in the case of a territory that's of a given size, the height of the S curve is anticipated in a trivial manner by the size of the territory that's to be bathed. So, contrary to my drawing here, all roads lead to Rome. All S curves rise to the same size, which is L squared. So let's begin the story of facilitating and obstructing with that joke. I'm going to erase now. Okay. So we have the time here and the area we have the ceiling, the plateau, that's known will be L squared. And of course, both area and time increase from 0. We know the shape of the curve. And the question is, do we allow this growth to be this way? Or is it in our interest to accelerate it? Or decelerate it? Now, why have this freedom to contemplate these two extremes, when in fact the result at the end of the universe is well known? Why? Because life is short. So here we are, and science is about us. We're interested to know because now in our lifetime we would like to have more of what is spreading and less of this toxicity that is spreading. That is the reason for contemplating the two directions, the two seemingly contradictory directions of usefulness. Well, the trivial way in which to turn the knob of the physics to do either Roman 1 or Roman 2 is to engineer the material, to modify the material through which the spreading is happening. That can be done by adjusting two parameters, because right now in this analysis there's just there are basically three parameters. There's the speed of invasion, there's the diffusivity, and then the size of the territory. We'll keep the size out of the discussion, because without picking an L we cannot make a drawing, or we cannot choose a page on which to make the drawing. But the other two depend. They depend on the initial speed of the rushing water into the channel. And obviously this alpha refers to the material, to the medium through which the spreading is occurring. So you see now from, you can actually, as homework, operate with the formulas that I put on the blackboard to see what you would have to do to, meaning how to change these two parameters so that you're either in regime 1 or regime 2. Without going through the mathematics, I can argue with confidence that clearly the steeper S curve happens when this speed of evasion is greater. So let's just talk about Roman 1. A greater speed makes the spreading faster, and then in the same direction, a greater diffusivity makes the spreading faster. And then the opposite holds for this other direction of daydreaming toward usefulness. Now, I've been using the river basin as a metaphor because with that kind of an imagery, I cannot be contradicted. If you don't know rivers, you were not even born yesterday. You were just not born. Okay, so everybody knows rivers and muddy banks. But the metaphor is valid for everything that behaves with its history and future in S-curve fashion. For example, the spreading of a population that is empowered by an idea, or empowered by possessing a particular gadget that's powerful in comparison with the gadgets that the rest of the territory possesses. So here's a territory that originally possesses only pencil and paper, but this new population that is invading from we all know from one point are those who have iPhones. So the invasion of the iPhone people is happening through channels, and these channels are invaded with a particular speed. For example, plane loads of iPhones are arriving from Taiwan and China to supply the Apple stores. The bigger and the faster they come, the more these, of course, and the greater the publicity that the Apple company makes, the greater these channels get filled. What happens? Well, in the immediate vicinity of those channels, meaning the universities and the businesses in the same shopping center as the Apple stores, are the first portions of the riverbank that gets wet. So proximity to the invading channel is the beginning of the consolidation or the spreading of the empowered population over the rest of the territory. It takes a while for the phenomenon that began, say, with iPhones spreading on the Duke campus and in the shopping malls of Durham, North Carolina. It takes a while for the same phenomenon to reach the university and the population of Ouagadougou, Burkina Faso. I've been there, and I've taught there, and people have iPhones. But I know that they first invaded, say, Durham, North Carolina. Probably even earlier, they invaded Taipei and Beijing. Absolutely. You see, so a very simple problem that everybody can solve once they are clever enough to formulate the problem is opening eyes of all sorts of types all over the globe. So that's about the spreading of a product. It happened in my own upbringing during my school years, where I was working with pencil and paper. All of a sudden, the big pens arrived. Big. They came from France. Well, the first people in town who got them were the people who had somebody they knew were relatives in France. They were the channel, and they made money by getting these presents from their relatives and selling them to their friends, meaning Adrian, and on and on. Of course, now the big pen is derisory. You use it, of course, you throw it away, but now everybody has access to a free big pen when they go into the bank or the doctor's office or wherever they have to sign a bill statement. That's again, I'm giving examples that illustrate the universality of the phenomenon. The phenomenon is called the S-curve, but I like to call it predicting the past and future of anything that spreads or is collected. Of course, collecting is the same thing. Here is a sketch of how oil is, here is the structure that holds the pump and all that, and the shaft that penetrates deep underground and sucks the crude oil upward. That's collecting. It sucks it how? Well, it sucks it from the finger-shaped region that's wetted, if you will, by the flow that's being sucked in. This is that region, sucked into this river channel of crude oil. I'll return to this example a little bit later, but instead of imagining oil extraction viewed in the profile, this could be the plan view, meaning the view from above of those of you who grew up in a village. the plain view of how grain is collected from this field. The field is this. This is the little dirt road on which the truck that collects the bundles of whatever is being harvested is traveling upward to exit from the field and join other such collecting dirt roads and vehicle everything away to the mill, to the flour mill. So that's collecting, but the architecture of the flow is the same as what we've been examining here. All right. This is again not exactly the end of the story. It's not the beginning either. The beginning is what led to predicting the S-curve in general. And okay, finally, there is another way in which one can manipulate answers to these two desires, particularly answers in the direction of accelerating or facilitating the spreading. The clever way is, which by the way, the clever way, cleverness belongs to nature. This other way happens by itself. It happens to people unwittingly, because people are actually part of nature. Is that the area that we've been contemplating? Now, that is, if I is a desire or an objective or a direction shared by everybody on the area, then the area develops channels that are not singular and needle-shaped. The area develops branched channels. Branched channels so that in the beginning, during the invasion, the more and more of the territory is covered, obviously like the cuts made by a knife, covered by more channels. So if the number of channels is called the K, say one such channel, and then if these two exist, then that's two, and then a three, and a fourth type. Then, of course, each channel develops its own fingers of original witness. That's one, and here's another finger, and another finger, and so on. If that's the case, then the S-curve that emerges is one that, so that's K. The S-curve that emerges is one that rises faster and faster. The number of channels K increases from 1, which was in the original example, to 2, 3, and 4. So again, because life is short, if you're interested in having more iPhones during this particular school year or Christmas season, when you're here in time, then you don't have to tell the Apple company. Apple company knows that it must have a better and better distribution or network of distribution architecture. So the reason these architectures emerge is because of the wish or tendency or attitude of every point on the area, of every individual in the population. Design for organization this drawing that you can make is emerges naturally because a multitude of invisible individuals share one desire or one need in common. The need of the wet plain under the rain is to get rid of the water. Or for that matter, the need of the sea is to get the water back because the rainwater originally came from the sea through evaporation. And from that you can reconstruct everything you know about geophysics. So with this, I say goodbye until we meet on the camera next time, which will be the 8th of April. Be safe.